A part of this talk, which is technical part, will be talked by him, Sumida. Well, here's today's agenda and introduction. Before talking about RapTapBath system, we should explain the Japanese bathing style. In most countries, to wash a body is usual and an important thing in the bathroom in everyday life. Japanese people have one more important thing to take a bath. It's to get warm by dropping into a bathtub for a time. The time for staying in the tub is depending on the person. Some people staying in for a few minutes or 10 minutes. Some people meditate, reading books, or sing a song, listen to music, or do something to have fun while staying and getting warm in the tub, everyday life. Also, Japanese children and parents get warm together in a tub, and they count numbers together to get out the tub, ask riddles and answer, play together in a tub. And so that the general bathroom in Japan is separated into two areas, a bathtub and a washing area. This washing area is kind of a Western-style shower room. On the other hand, these generic Japanese bathrooms have some issues of the user interface related to equipment. The basic issue is the location of a remote controller of equipment, such as a water heater. Most of the controllers are attached on the wall and fixed locations. Then we cannot reach it easily, even though in a bathroom. A bather may need to twist the body or reach forcibly. I guess it's inappropriate, especially for elderly or people with disabilities. It's a kind of issues of physical usability or accessibility. The second issue is the increasing controllers. For instance, of this picture, water heater controller, audio, lighting, heater dryer, and mist generator. Well, unbelievable. I guess it's so ugly, these controllers attached on the wall. It's also a looks issue. Then we aim to resolve these user interface issues by providing a universal interface for Japanese bathroom. Especially, we have focused on retrofitting to existing bathtub. This figure is a top of view of generic Japanese bathroom. There is a bathtub edge as a center area of this bathroom. This part can be used for universal user interface. So we have installed sensors inside of this. There are our previous works for bathtub edge user interface, rubbing UI and touch UI. Both of them have sensors inside of the top of bathtub edge. Today's talk about RapTapBath, which is a tap user interface system with embedded piezoelectric sensors attached inside of the bathtub. Please watch this video. Tap location detection and tap tones identifying and recognize tap patterns. This system can be for controlling existing equipment and also providing a novel application for the use while bathing. Well, that's a system overview about hardware stuff of the RapTapBath. A lot of Japanese bathtubs have a removable side panel to access inside of it, like this. And so we can attach piezoelectric sensors inside of top of bathtub edge easily. These sensors capture tapping sound as acoustic signals through the bathtub. Also, application screens is projected from the ceiling projector installed on the bathroom ceiling. There's enough space around the ceiling dryer to put a projector above ceiling. We think it's important that these sensors and a projector can be set to existing bathroom. As software staff functionalities, this system can deal with tap location, tap tone, and tap pattern via signal processing technique in real time. The UI events from these blocks utilize as a combined or an independent event to operate equipment or various applications. So here, switch to him.
Well, from these slides, I'll explain tap UI events. Those are viral in RapTapBath with each process methods. The first is about tap location detection. This figure shows the overview of detecting a tap location with only 2 sensors for simple explaining. We attached 4 or 5 sensors in one bathtub edge at regular interval. It's easy to install sensors into existing bathtub. The method of detection of tap location is simple. It uses the difference of signal arrival times between sensors. The signal arrival is the detection of initial vibration caused by tap on each sensor. We use running RMS, root mean square method, which is based on short-term integration of square signals, and also use appropriate thresholds for each sensor by calibration. This research uses the same method applying for 2-dimensional location. Our location detector is for 1-dimensional location because of a narrow area to tap. This shows distributions of propagation time of initial vibration with a real bathtub edge in our smart home environment. Horizontal axis is the distance between a tap location and a sensor. We can see that distributions under 300 millimeters are not overlapped. So it means that the regular interval of piezoelectric sensors is 300 millimeters. We can detect a tap location at 100 millimeter intervals. The second tap event is about tap tone. Tap tone identificator can handle 5 tap tones caused by these hand posture, fist, knuckle, pad, tip, and fingers. And also, we add the noise sound to identify in case a user hit the body to a tap unintentionally. The frequency components of each tone are like these spectrograms. Low frequency components of all sound are relatively strong. High frequency components may be absorbed by the material property of bathtub, but we can see the specific features contained in the high frequency components. So this tap tone identificator filters low frequency components below 5 kHz with high pass filter. There are few related works. These systems use SVM, support vector machine, to identify tap tones on the 2-dimensional plane. But in our research, we don't use SVM, but NMF, non-negative matrix factorization, which is a kind of machine learning techniques. NMF is an algorithm which can separate non-negative matrix, such as a spectrogram or image pixels, into a feature matrix and coefficient matrix. In our case, we are applying this NMF technique to tapping sound on bathtub edge. In this figure, our input matrix is only a latest FFT frame. It's a instant power spectrum. The duration of tap sound is too short, and also it should be identified in real time. That's the reason why our tap tone identificator uses only the latest power spectrums. So in general, NMF is used for source separation in sound signal processing. An input spectrogram is separated into dictionary matrix, which is shown as H, created as a template of per spectrums of each tone, and also separated into excitation matrix, shown as U. The excitation values in the matrix U are corresponding to each per spectrum. So, excitation values of templates registered in the dictionary matrix are calculated iteratively by updating only the excitation matrix. Finally, the result from this excitation value are used for source separation in general NMF. In our RapTapBath, our tap tone identificator chooses the highest excitation value with input power spectrum's power as an identification result. This slide shows evaluations of current tap tone identificator. This evaluation uses tap sounds recorded 100 times by 5 male subjects for each of 5 tap tones. This red line and dots show a result of user-independent evaluation with 5 subjects. The horizontal axis is the number of combinations of tap tones. This shows that less number of combinations is more accurate. The next is blue line and dots show a result of user-dependent evaluation. It shows that user-dependent identification is generally more accurate than user-independent. In addition, we also evaluate noise immunity using signal depth while basing over 20 minutes. The evaluation used the NMF, added a noise template, and tested with all the combinations. The result of accuracy is about 90%. By the way, we'll show you a recent evaluation result with a trained neural network, which is not described in this paper. Please look at this as off-topic. The result of all of a combination are higher than 97%. We depressed what is our hard work for NMF. The last tap event is tap pattern. Tap pattern recognizer carries a time series of taps in a specific period as an event. In this research, this recognizer can handle various patterns of plural taps, but many people can't use over 4 tap patterns. Only musicians can use. Then 3 tap patterns should be assigned to operations. This shows an example of recognition process for a pattern of 3 taps. At first, 3 taps in specific time period are detected. Tap pattern recognizer normalizes the time scale between the first tap and third tap for pattern recognition. And then the normalized time of second tap is calculated and refer to probability density functions for each tap pattern. Finally, a pattern which has the highest probability at the time of second tap is selected. These are the estimating method for tap pattern recognizer. There are 3 patterns or 3 taps shown in previous slide. We set the probability density functions as Gaussian functions for each pattern. Each Gaussian has a specific mean and variance. Those are obtained and calculated by real taps previously. First, 3 consecutive taps are shown such as Gaussian distribution. The second pattern are shown such as distribution. The third pattern are shown such as distribution. As a result, it is estimating that the 3 consecutive taps is likely tap patterns.
Well, oops, sorry. After the applications, so That first, that dimming light operated by the tap pattern. That we think that assigning this bad example seems not intuitive for operation. And the next is a music player. This example is also use of tap pattern, but this is not so bad. Even though while washing your hair with closing eyes, we can tap to control. Everyone have an experience to play whack-a-mole. Maybe it's an effective video game for children who don't like taking a bath. The percussion instrument. So we demonstrated this at the ACE conference in Osaka last year. And it's a simple function of quiz buzzer. Thus, for riddle and answer. Sorry for that. We couldn't arrange a Japanese model family. So in this video, played by graduate students. Yeah. And we try to make an input method for Japanese characters by tap tones. I guess voice input is better. Also, we overdo to make an input method for Japanese character by Morse code, the tap pattern, tap tone. So discussion, so time limitation. One of the implications is we should think the life cycle of housing equipment is decades. It's relatively too long. We usually change smartphones every 1 or a couple of years, and electric equipment such as refrigerator or washing machines every 10 years. So retrofitting is so suitable for existing bathroom to change our smart environment. And limitation to this use of tap sound precedes specific limitation stuff in your paper. And interactive design issue is the most important step for useful practice use, we think. Our current work is for these issues, design and implementation and evaluation. So, conclusion, we proposed and implemented a tap user interface as a RapTapBath as a universal user interface for real bathtub environment. Then future work. Thank you for your attention.
Thanks a lot. Thanks a lot. Really, really nice. We've got time for a quick question, and maybe we could have like our next speaker setting up already. Okay. So if anyone is curious about it, yeah.
Hi, Benjamin from University of Stuttgart. I have a question. Did you try to also do the tapping inside of the bath, so to the side wall, and not just on top, so you don't have to leave the water?
Pardon me, that?
Tapping on the side of the
side.
bathtub? Yeah.
That's okay.
So it also recognizes same, because it's from a different state, maybe it's more different tone?
It's not same on the side panel, but some events can recognize that.
Okay, great, thank you.